This video is going to walk you through the process of constructing and completing a truth tree. We're going to focus on, first, what does the truth tree do? And then, second, we'll look at the actual process of starting out your list at the top of your truth tree, and then using the 9 decomposition rules to simplify all of your compound formulas. And then third, we'll look at how to recognize contradictions in your truth tree, which close specific branches. In the next video, I'll discuss the differences between the truth tree test for consistency of a group of statements and compare that to the truth tree test for the validity of an argument. Before I jump into the details, please note that the truth tree assignments that have been posted, some students have had issues properly seeing the symbols in those assignments. This occurs when you use a word processor program like Text Editor that can't display the horseshoe or triple bar sign. Microsoft Word and Google Docs does display all the symbols properly. If you're worried that what you're looking at doesn't match what you should see, I have uploaded PDF previews for each of those assignments on each assignment page. So if you scroll to the bottom of the page, you should be able to scroll up until you see the questions, and that'll appear the way that you should be seeing them in whatever program that you're using. So let's begin by examining what a truth tree does. And we're going to look at first applying the truth tree to a single formula. So on the next page, I have an example formula, P and not P. And what a truth tree does, it shows us whether it's possible for that formula to ever be true. This formula is a conjunction. The dot is the major operator. So the truth tree is going to tell us whether that dot operator can ever output a true value. Now, when I start a truth tree, the first thing I always do is rewrite the formula or all of the formulas. Here we only have one formula that's been given to us. That's what we're trying to test. So I wrote given over to the right. Now, since it's a conjunction of the 9 decomposition rules we have for how to break down compound formulas, we want to use decomposition rule number 2. In decomposition rule number 2, I've taken a screenshot of it. So I'm just going to drag it over to the right. And here's how to read these decomposition rules. You have these lowercase letters, and they represent any formula, any well-formed formula. And we have a pretty simple formula here. It's telling us, okay, P is to the left of the dot. And in our example formula, the lowercase p corresponds to an uppercase P. And the decomposition rule is telling us to take what's to the left of the dot and copy it directly below. The lowercase q represents whatever's to the right of the dot. In our example formula, I'll give us a little space here. In our example formula, what's to the right of the dot is not P. So that's precisely why Q in the rule schema corresponds to not P. And this is telling us copy whatever's to the right of the dot and put it right below that lowercase p formula. So the next part of our truth tree, we should follow that pattern that the rule showed us. I'm just going to copy and paste. This is the correct application of rule 2 for this formula. Whenever we're doing a truth tree, we're always looking for contradictions. We want to see if we have a letter and the negation of that letter. If so, then the branch closes. And sure enough, on lines 2 to 3, we have P and not P. That's a direct contradiction. It's incoherent, so the branch closes. And put an X. It's a little easier if you're doing this by hand. This is the only branch of this truth tree, so we're finished. The only branch is closed. That means we don't have to do anything more. Let me shift this around. So the only branch on the truth tree closes, and since there are no open branch, it shows that it's impossible for the original formula, P and not P, to be true. An easy way to double check your work you can do, in this case, a truth table is very simple. I'll do a version of the truth table. We only have one sentence letter in this formula. So there's only two possible truth values. Either P is true. It should be an uppercase P, not a lowercase p. So let's see what happens if we assign true to P. Left side of the formula comes out true. Right side, we also assigned true to P. But notice on the second level, the negation sign flips the truth value. And when we're evaluating the dot operator, we need both sides to be true in order for it to output true. That didn't happen, so sure enough, it outputs false. What about if P is false? We can easily recreate that possibility as well. So if P is false, then the left side of the conjunction is automatically going to be false, and that's going to make the entire formula false, even though the right side does come out true. To sum up, us double checking our truth tree work, neither of the two possible inputs for that formula, P being true or P being false, makes the formula as a whole, the conjunction, true, which is another way of saying it's impossible for the formula to be true. There are no open branches. And in this case, it's obvious why this formula can't be true. It's asserting two contradictory things, P and not P. So let's now apply a truth tree to a group of formulas. Here I have an example of a group of formulas that has two formulas. They're separated by commas. And I've started the truth tree. First line, P or not Q. That's our first given formula. And Q or not P. That's our second given formula. So when we apply a truth tree to multiple formulas, what we're looking at is, can all of these formulas be true at the very same time? Can they simultaneously be true? Now these two formulas have the same major operator, disjunction, so we're going to use the same decomposition rule to break them down into individual letters. So when we have a disjunction, the wedge, the decomposition rule tells us whatever's to the left of the wedge, this lowercase p, copy it under a left branch. Whatever's to the right of the wedge, lowercase q, just copy that down below the right branch. Now, when we apply the decomposition rule to line 1, the left side corresponds to uppercase P, while the right side, the lowercase q, corresponds to not Q. The first application of decomposition rule 2 is going to look like line 3. I copied what was on the left side and I put it under the left branch. I copied what was on the right side and I put it under the right branch. Notice, even though there's no negation signs in the decomposition rule, you should read this as saying copy whatever's there, no matter what the symbols are, just strictly copy and paste it down. So you need to have that negation sign, negation Q, because that was what was in the original formula. Now we need to apply the same decomposition rule to the formula in 2. And here's another important point. This formula is above 2 open branches. So when we apply the decomposition rule to line 2, we actually need to write it under both open branches. We need to write it twice. A lot of people are tempted when they're first doing truth trees to just split the difference and throw it in the middle. But the reason why you can't do that is as your truth tree gets bigger, when you have larger formulas, it becomes ambiguous what is under what. The whole point of splitting branches is to show that these are independent destinies. They're independent ways of trying to make all these formulas true, so it's crucial to explicitly show what is separated from what. So on line 4, this is our second application of the decomposition rule. I've copied the left side on the left branch. I'm doing it twice under each open branch. And I copied the right side under the right branch. Now we look for contradictions. Q doesn't contradict anything, so that's an open branch. Not P, that contradicts P, so that closes. Q contradicts not Q, this branch closes. Not P doesn't contradict anything. So the final result, we see that in this truth tree, we end up with 2 open branches after we've broken down both of our compound formulas, and 2 closed branches. Now all we need is 1 complete open branch, and that's enough to conclude that the formulas are consistent. So these 2 formulas can be true at the same time. This is precisely what the truth tree is showing. And furthermore, we can see by reading off these 2 complete branches here and here, this first possibility, Q is true, P is true. That's reading this first open branch. If you insert those values into these formulas, both are going to come out true. Or alternatively, reading the rightmost open branch, P is false and Q is false. And that will also make both of these formulas true at the very same time. So 2 independent ways of making these formulas true, and thus showing that they're consistent. If you have any doubts whether this is actually working, you can look at these 2 formulas using the truth table method. So here I've handwritten a truth table for these 2 formulas. We have 2 sentence letters, so we need 4 rows. And if we look across, this is how the truth table matches up to the truth tree. We can see here are the major columns in boxed green for each of the formulas. And you ask yourself, when are they true at the same time? Well, we see on the first row, true and true. And here are the inputs for the 2 letters. Both were true. And that corresponds to this leg of the truth tree. The only other time both of the formulas come out true at the same time is when this bottom row, true, true, both were inputted as false. And this line of the truth table corresponds to the rightmost open branch. So this is a very simple example of what it means to apply the truth tree method to a group of formulas. We're showing whether these different formulas can be true at the same time. Now that we've seen a couple of simple examples of truth trees and covered at its most basic level what the truth tree does, let's now focus on the distinct steps of completing a truth tree, beginning with how you start a truth tree. So we're looking at the different steps it takes to complete the process of a truth tree. The first, the beginning of a tree, you either have a single formula or multiple formulas. And the first thing you need to do is list out all of those formulas and put them on top of each other, stack them. These are 3 problems from exercise 3. Problem number 2 has 2 formulas. You stack them right on top of each other. When you stack formulas in a truth tree, you're saying, I want these to be true at the same time. Problem 3 has 3 formulas, so we have 3 different lines. Problem 4 also has 3 formulas, so we've stacked those 3 formulas right on top of each other. So now that we've covered the beginning of the truth tree, let's now take a look at the middle of completing the truth tree, the most important part, applying the decomposition rules. So the decomposition rules tell us the minimum required to make an operator true. We apply the decomposition rules to compound formulas in order to simplify the formulas, and we want to apply those decomposition rules until we've isolated the letters or negated letters that are the fundamental building blocks of the formulas. As mentioned before, there are 9 decomposition rules. We have 1 for every 2-place operator. That is, every operator except the negation sign. We also have rules for every negated operator, and this includes the double negation, which is simply a negated negation sign. So as we work through more example problems, I'll refer back to these patterns. And these are all that you need, these 9 patterns, to break down the biggest, most complex formulas until you're only left with letters and negated letters. So to demonstrate the process of applying the decomposition rules, let's return to problem number 2 from exercise 3. We saw a few slides back the beginning of the truth tree. So we copied the 2 formulas and stacked them on top of each other, and that's the beginning of our truth tree. Now, when you're applying the decomposition rules, you can go in any order that you want to. You don't have to start with one, but in general, it's better if you do stacking rules first because it saves you time. You have to write down fewer formulas if you break down the operators that will stack. So of these 2, the dot rule stacks, so I'm going to apply the decomposition rule for that first. So to the right, you can see decomposition rule 2, the dot rule. Here's our major operator, so that's how we know it's the one that fits with formula in line 1. And we copy what's on the left side right down below the dot, and we copy whatever's on the right side right down below that other formula we copied. Stack them on top of each other. So when we apply that to t dot s, we end up precisely with t over s, both from line 1. So we have one other decomposition rule left on line 2, the conditional. So we need the decomposition rule that corresponds to the conditional, and that is rule number 3. And what rule number 3 tells us, when we run into a conditional, we want a splitting tree. And whatever's to the left of the horseshoe, we're going to copy and then add a negation sign to that formula. Whatever's to the right of the horseshoe, we're going to copy and directly paste it to the bottom of the right branch. On line 2, the formula that corresponds to the lowercase p, the formula left of the horseshoe, is not s. The formula to the right of the horseshoe, where the lowercase q is, that is not t. All right, so we're still looking at line 2. So when we apply this decomposition rule, we should end up with one line, line 5. So when we apply the decomposition rule for the conditional to the formula in line 2, we take the not s, put it on the left branch, and we add one negation sign to it. That's how we follow this pattern. Copy, add a negation sign. We take whatever's to the right of the horseshoe, and we directly copy it to the right branch. This is the correct way, line 5, to break down the formula in line 2. Now, every time we apply a decomposition rule, we want to keep an eye out for any contradictions. Here on line 5, we have not s. That does not contradict s. Right branch, we have not t. That does contradict t. So the right branch closes. And here's what applying the double negation rule to line 5 looks like. We get s, we get to eliminate both of the negation signs, and that makes it clear that s does not contradict s. At this point, we've broken down every compound formula in our tree, and we see we have an open branch. So that means with an open branch, all the formulas that we started with can be true at the same time. In other words, they are consistent. And to read off the truth values from this open branch, s is true and t is true. When we input those truth values in these 2 formulas, we're going to get a true conjunction, and we're also going to get a true conditional. Everything that I've just explained in doing the second problem from exercise 3, you can see spelled out in this fairly large paragraph. The most important point, the one I want to emphasize the most, when you see these lowercase p and q letters in the decomposition rules, treat them as stand-ins for any well-formed formula. It could be a really large formula. They are variables. They are not themselves formula. When you understand that these are variables that stand in for any well-formed formula, you're going to better be able to follow the patterns of these decomposition rules. So we've covered in detail how to apply the decomposition rules, how to recognize those patterns, and how they fit the formulas you're going to run into. The third basic part of the process, how do you close branches? So we only close a branch of a truth tree when we have a contradiction. Contradictions close branches. To get a contradiction, in the most simple terms, you need a letter and you need the negation of that very same letter. Now, to put some flesh on this point, let's take two different letters. And remember, this gets back to the basics of propositional logic. An uppercase letter represents a single declarative statement. Let's say that K represents the statement, I drank coffee this morning. Let G stand for, I went to the gym this morning. Now, look at the following truth tree. This is from Appendix B of our textbook. This is a completed truth tree. The left branch is still open. The right branch is closed. Now you might be wondering, how is the left branch still open? We have not K here, and if I go up the tree, don't I see K on this line, line 3? Don't I see K on line 2? Don't I even see K on line 1? So why isn't this also closed? So let's look at this not K and the K that's up here on 2. This is not a contradiction, and the basic reason why, line 2 is not asserting K. Line 2 asserts if K, then G. To paraphrase, this means that if K is true, then G is true as well. To use our example sentences, imagine me telling you that if I drank coffee this morning, then I went to the gym. But if I phrase it like that, notice I'm not guaranteeing to you that I actually drank coffee this morning. And that's the semantic reason why not K, that is, it's not the case that I drank coffee this morning, does not contradict the sentence, if I drank coffee this morning, then I went to the gym. Now, look at the right branch. Line 5 says not G, whereas on line 6 of the right branch we have G. This is the same thing as saying on line 5, I did not go to the gym this morning. Then on line 6, I went to the gym this morning. These two assertions are obviously incompatible. Either I went to the gym this morning or I didn't, and that's precisely why this branch closes. They directly contradict each other. To summarize our discussion of how to find contradictions in truth trees, the first bullet point, look for contradictions between a letter on a line by itself and the same letter negated, such as K and not K. And you want both of those to be on lines by themselves. That gets into the second point. Do not count it if the letter is part of a larger formula. Also, only go up a branch when you're looking for contradictions. In this case, when you start with the left branch, not K, and you are looking for contradictions, you can only go up. You cannot go back down a line because the whole point of branching is, again, to represent independent destinies. So that would be ruined if you're going up and down branches. In conclusion, we reviewed what exactly a truth tree does. It shows whether a formula can be true, or if we're dealing with multiple formulas, if all of those formulas can be true at the same time. And we also went into the specifics of the process, how to start a truth tree, how to use the decomposition rules to simplify the compound formulas, and how we close branches. In the next video, I'm going to discuss how the truth tree test for the consistency of a group of statements compares to using the truth tree to test an argument for its validity.